So we're very pleased to have Tatsuhiro Misumi from Akita. Fire away, Tatsu.
Okay, thanks so much. Thanks so much for the introduction. So can I start? Okay.
Yep, please.
So I'm really happy to have a chance to give a talk here. I really appreciate the organizer's invitation. And today I'm going to discuss resurgent structure and adiabatic continuity in the QFT with the twisted boundary condition, with mainly focusing on the recent progress since 2017. And this talk is based on the several works in collaboration with these people, including KO and Yuya and Mitat. I think Mitat are also here. Okay, so let me start. Oh, doesn't work. Okay. So the main theme of this talk is the twisted boundary condition, which I will discuss in detail later. And here I just make some comment on the conjecture called adiabatic continuity. It states the vacuum structure and ZN symmetry persists or survives during ZN twisted boundary compactification, ZN twisted compactification. And the basis of this argument is fractional instantons cause tunneling transitions among classical and minima, and it makes ZN symmetry stable, which leads to the volume independence of the vacuum structure. And regarding this ZN twisted boundary condition, there are some prospects and known facts. So firstly, the resurgent structure on compactified space-time may continue to decompactified theory. And the second one, secondly, weakly coupled weak coupling confinement, which is called bion confinement, may be connected to the strong coupling one. And thirdly, adiabatic continuity in two-dimensional sigma model is exactly proved in large N limit, and the Hooft anomaly of that model is also shown to survive with the twisted boundary condition. So in this talk, I will discuss the conjecture itself and the resurgent structure in the mainly 2D theory with the twisted boundary condition by using a couple of tools, including semi-clasks, anomaly matching, and lattice simulations. So this is a plan of my talk. Firstly, I will discuss the resurgence and bions in the twisted CPN -1 model. And to discuss adiabatic continuity in CPN -1 models in the third section, I'm gonna give a very brief review of the Hooft anomaly and the related lattice simulations, where I take the twisted 4D gauge theories as an example. And this theory itself is interesting, so I think it's worth discussing it here. And if I have extra time, I will discuss other theories with the twisted boundary condition, where the adiabatic continuity can be shown exactly. So let me begin with the CPN -1 model. So for simplicity, let me focus on CP1 model for the first time. And this model is an asymptotically free theory whose target space is CP1, homeomorphic to S2. And here I write down the Lagrangian by the inhomogeneous coordinate, phi, and I also introduce the fermion term too. And so we consider R cross S1 space-time, and we impose the two twisted boundary condition on the theory, on the field like this. The L is a compactification circumference, and this ML is a twisted angle, which is given by pi over L for Z to twist. And with this boundary condition, this model has exact Z2 symmetry, which plays a very important role in the discussion of the Hooft anomaly. And what is interesting with this boundary condition, the theory has fractional instanton solutions with fractional topological charge and fractional action. And they map the space-time out close S1 to the half of the target space in this case. If for generic n, so it maps the space-time to the 1 over n of the target space. And before looking into the 2D theory, we warm up with CP1 quantum mechanics, which can be roughly regarded as a compactified version of this model. And this is the Lagrangian, and we put one parameter, epsilon. When epsilon equals 1, so the theory becomes supersymmetric quantum mechanics. And since Hamiltonian and fermion number operator commutes, we can consider the zero fermion number sector or the subspace of the Hilbert space. Then we can obtain the effective bosonic theory with this bosonic potential, And in this theory, I want to note it has two local minima, which is corresponding to north and south poles. And if we take epsilon equals 0, which corresponds to bosonic theory, so it has instanton solutions describing the tunneling between two minima. And this is nothing but a remnant of the fractional instanton in 2 dimensions. And with non-zero epsilon, so it has a special solution called the bion solution. There are two types of the bion solution. One is the real bion solution, and which is expressed as shown here. And it has two moduli, position moduli tau 0 and phase moduli phi 0. And this is a kink profile of the process of the vacuum transition, minima transition. And the point is the distance between the two constituents, instanton and anti-instantons, is fixed. But this distance, relative distance, I will discuss that this distance is called quasi-moduli, which plays an important role to obtain the contribution from this solution. And we also have another solution called complex version of the bion solution, complex bion solution. In this case, we complexify the variable, and the theory becomes T star CP1. And so the phi and phi bar are independent variables. So I write it phi and phi tilde here. And the solution is given by this form. And in this case, kink profile or the vacuum transition is given by like this. And it takes the complex detour like that. And in this case, the distance between the two constituents are complex. So it has a complex relative distance. It's quite special. And we can extend it to the multi-bion case. And we have the multi-bion solutions. And these are solutions, and it is mainly given as an elliptic function. I don't have enough time to discuss it in detail, but the main point is these solutions are classified by the two integer Q, P, and Q. And for PQ equals 3 and 1, the kink profile or the transition process is given by this kind of form. And this expression gives an infinite tower of the multi-bion solutions. And their contributions are calculated by quasi-modular integral, which I will discuss in the next slide. And the solution, the contributions from real and complex bions canceled out for supersymmetric case. So let me discuss the quasi-modular integral. So to obtain the contributions from the bion solutions, we need to perform the quasi-modular integral. And what is quasi-moduli? So quasi-moduli parameters correspond to nearly massless modes or nearly flat modes, which will become true moduli or true modulus in G square to G square 0 limit. And so in this case, we have two kind of the moduli parameters, quasi-moduli parameters. One is instant anti-instant distance, phi r, and the other is the relative phase, phi r. And the existence of these modes means one loop determinant calculation is not enough to obtain the contribution from these solutions. So because we have nearly flat direction for the solutions. So the contributions from real and complex bions is mainly given by this kind of integral, where the effective is an effective potential in quasi-moduli space, or the effective action in the quasi-moduli space. It is given by this expression in this case. And the point is, in this case, we complexify the variables in the theory. So we need to deal with these two parameters as the complex variables. So this is the point we rely on the Lefschetz-Tembo integral method. In this case, the original contour path, contour is decomposed into multiple Tembo contours or Tembo cycles, where n sigma is intersection number between the original contour and dual Tembos. And both Tembos and dual Tembos can be obtained by solving the flow equation. And in this case, we complexify the two variables, so the space becomes 4D space. And the Tembo and dual Tembos is now the 2D surface, the two-dimensional object or the 2D surface. And this is a 3D projected space of the 4D space of the tau r and tau phi r. This is depicted in the space of phi imaginary, phi real, and tau imaginary. And this is the appearance of the Tembos and dual Tembos and the saddle point and original contour. And these four black points indicate the saddle points. And these two are the real bion saddles, which are equivalent because of the periodicity. And these two correspond to complex bion saddles. And these four straight line, red, blue, yellow, and green ones are Tembos associated with four saddles. And four surface, red one, blue one, yellow one, and green one are dual Tembos. They are also associated with four saddles. And this orange line is original integration contour. So in this case, blue and yellow dual Tembos intersect with this original integration contour. And in this case, we consider argument G square is smaller than 0. And so in this case, the intersection number for these two Tembos are non-zero. But if you consider argument G square larger than 0, red and green dual Tembos intersect with this original integration contour. So there is a Stokes phenomenon. Okay, and this is a whole, how to say, structure of the this Tembo and dual Tembo structure, and there you can see the point of the intersection. Okay, so now each integral along with each Tembo can be calculated easily, and we obtain this expression. And intersection number, we also find the intersection number between the original contour and the dual Tembos, which are given by this number for argument G square smaller and larger than 0. So there is clearly Stokes phenomenon, and which leads to imaginary ambiguity of the physical quantities from these bion solutions. So let's look into the bion contribution to ground state energy, where we define the delta epsilon, which is given by epsilon minus 1. So delta epsilon means a Suji breaking parameter. If the delta epsilon is 0, so this contribution to energy becomes 0 because of the cancellation due to Suji. But here we expand this quantity with respect to this delta epsilon, and we can obtain the first order coefficient or the second order coefficient, blah, blah, blah. Then we find the second order coefficient of the ground state energy with respect to delta epsilon has imaginary ambiguity. And we can extend or generalize this discussion to p-bion cases or the p-bion solution, multi-bion solution. Then we obtain the same kind of the coefficients. And in this case, again, the second order coefficient include imaginary ambiguity with this p-bion action factor. So let's look into this fact from the viewpoint of the exact result. So we can calculate the second order coefficient of the ground state energy with respect to delta epsilon, as shown here. And below, we will write it in a transeries form. So first, we will extract the perturbative part from this exact form in asymptotic form, which is given by this expression. And it can be also calculated by the Bendel method too. And the residual part is non-perturbative part, and it is also given now in asymptotic form. And here we take Borel resummation, then find it has singularities on the positive real axis. So both of them have imaginary ambiguity. Each of them has imaginary ambiguities. Like that. Then we can interpret them. So for example, this part is the perturbative contribution around 0 bion background. This is real perturbative part. And this part is a p-bion semi-classical contribution, which is nothing but the quasi-modular integral we have obtained in the previous slide. And this is a perturbative contribution around the p-bion background. And the point is the imaginary ambiguity of this perturbation is cancelled by that of the 1 bion semi-classical contributions. And the imaginary ambiguity of perturbation around p-1 bion is cancelled by that of the semi-classical contribution of the p bion. And it repeats to an infinite p, and we end up with the final exact result. So this is an example of the exact resurgence structure in which exact cancellation of imaginary ambiguities to all orders of the transeries is observed. Okay, now let's move to two-dimensional CPN-1 sigma model on our closest one with ZM twist. So here we again consider Suji deformed Lagrangian with this deformation term from the n equal 2 to CPN-1 Lagrangian. Here I will use the compactification radius instead of the compactification circumference for later use. And we again impose ZM twisted boundary condition both on bosonic and fermionic fields. And this theory with the ZM twisted boundary condition has the bion solutions, including real bion solution and complex bion solution. They are quite similar to the expressions are similar to those in quantum mechanical model. And they are composed of 1/n fractional instantons, and they are homogeneous in compactified direction. As shown in this figure, it is action density of these bion solutions, especially real bion solutions. So what we have to do is to perform quasi-modular integral to obtain the contributions from these solutions. So we have to consider effective action in quasi-modular space, and it is given by this form. It is also similar to the quantum mechanical one. And we call it as a bare effective action because it contains bare coupling here at this stage. And so the bion contribution to the partition function is obtained by this integral. But in this case, we have to consider the constant fluctuation from the quasi-modular space. We here consider small g square region, but we have to consider or take into account the constant fluctuation around the quasi-modular space. So we need to calculate this one-loop determinant for fermion and bosons. This J is a quasi-modular space volume. So what we have to do is to take a sum over KK modes of the constant fluctuation. Here we use a theta function regularization. And this is the results of the KK summed one-loop determinant. So it's a little bit complicated, but among them, I want to emphasize this part. Log of the KK sum of the bosonic determinant is mainly given by this form, and it contains the infinite sum over n KK index. So we have to use some regularization, and we adopt here Hooft theta function regularization, and we end up with this result. It includes the lambda 0 cutoff scale. So now we put this determinant part on the exponential. Then we define the renormalized effective action, which is denoted as SR, and which is given as S minus log n fermionic determinant and log plus log bosonic determinant. And by using the results in the previous slides, we obtained this result. And what is surprising is that in this renormalized action, the coupling constant becomes a renormalized coupling constant, which is given by this well-known form, or it contains dynamical scale. I want to emphasize it appears automatically only by considering the constant fluctuations. So by using this renormalized effective action, we can calculate the contribution from these bion solutions, as with the case in the quantum mechanics. And we end up with, for example, the vacuum energy from this bion. And this is given by this R lambda. Lambda is a dynamical scale of the CPN model. R lambda square, and it also includes the imaginary ambiguity. So we can say it is renormal or the renormal-like imaginary ambiguity, and it should be cancelled by the perturbative Borel resummation. So I want to emphasize it is a result related to the resurgence with renormalized coupling. And now the question is whether it is related to the IR renormal on R square. And there have been very intensive studies on this subject, including the work by the Kyushu group. And I also refer to the beautiful work by Marino Reis for renormals and resurgence in the other models. It has direct relation. It has no direct relation to this cross S1 case, but it is also important. And in any case, the key is whether the compactified theory is smoothly connected to the theory on R square. So this is the reason why I will discuss adiabatic continuity of Z and QFT by use of Hooft anomaly and lattice simulation from next slide. Okay, so let me review the Hooft anomaly and lattice related lattice result very briefly, where I will take the Z and twisted 40 gauge theories as an example. So what is the use of the Hooft anomaly matching? If we find a Hooft anomaly of some symmetry G at UV, it should be also in IR. So trivially gapped phase is forbidden. So there are only three choices, SSB of symmetry G or the part of the symmetry G in gapped phase, a CFT, or intrinsic topological phase. And in two-dimensional case, the choices becomes only two, the SSB of discrete symmetry or CFT. And recent progress of the Hooft anomaly is partly owed to the understanding of the higher form symmetry. And here I focus on the ZN one-form symmetry for the introduction. And as you know, the zero-form symmetry is nothing but usual global symmetry whose charged object is zero-dimensional point-like operator. And topological symmetry operator has a three-dimensional volume, which is associated with the net charge in this case. And this is the example of the ZN zero-form symmetry. And on the other hand, one-form symmetry is an invariance under transformation by the closed one-form, which is denoted as epsilon1 here, and whose charged object is a one-dimensional line operator like this. And the topological symmetry operator in this case becomes two-dimensional surface. And one good example of the discharged objects is a Wilson loop in SUN-Yamuse theory. When it is transformed non-trivially under this transformation, it obtains this nth root of unity. And it is the example of the ZN one-form symmetry. And the point is SUN-Yamuse theory has a ZN one-form symmetry, which is sometimes called center symmetry, at least at low temperature. So we want to discuss the Hooft anomaly of this symmetry. So the question is the way how to gauge such ZN one-form symmetry. The answer, or the answer is the introduction of the pair of the U1 two-form gauge field B and one-form gauge field C with this special condition NB equals DC. It is regarded as a higher form generalization of this relation between U1 gauge field and the Higgs scalar field in the low energy effective field theory of the Higgs vacuum in the symmetry with the symmetry breaking U1 to Zn. And by using these U1 two-form and one-form gauge field, we can have the Zn gauged action for the SUN gauge theory, where we define the UN gauge field A tilde, which is a combination of the original SUN gauge field and U1 one-form gauge field, and its field strength is denoted as G tilde here. And to make the whole action U1 gauge invariant, we have to consider the combination such as this G tilde minus B. And here we put the kinetic term and theta term, and also consider topological field theory term, which includes a parameter called discrete theta parameter P, which works as a coefficient of the counter term to get rid of the Hooft anomaly. So now we note ZN one-form symmetry itself is not broken in this action, so it has no Hooft anomaly. But there is some possibility that the CP symmetry may be broken in this action. In such a case, there is a mixed Hooft anomaly between ZN one-form symmetry and CP symmetry, and either of them should be broken spontaneously. And so let's perform a CP transformation on the action, and we find this kind of the non-trivial factor, non-trivial phase, as a result of the index theorem. And let's look at this part. So if n is even, it obviously has mixed Hooft anomaly. So there should be Hooft anomaly. And if n is odd, so there is some possibility that the Hooft anomaly disappears. For example, 2p minus 1 equals 0 mod n is possible. And in this case, there is no Hooft anomaly, but it's inconsistent. We are now considering theta equals pi case only. And so in this case, there is no Hooft anomaly, but it is inconsistent with the anomaly absent or anomaly free condition for theta equals 0, 2p equals 0 mod n. And we know that theta equals 0, there is no mixed Hooft anomaly between CP and ZN one-form symmetry. So it means theta equals pi case has mixed Hooft anomaly even for odd n. So this mixed Hooft anomaly and global inconsistency, this condition is called global inconsistency. Mixed Hooft anomaly and global inconsistency indicate the symmetry breaking, spontaneous symmetry breaking of either of the CP or ZN one-form symmetry, as long as the system is in a gap phase. And what is surprising is that this Hooft anomaly or mixed Hooft anomaly survives even in the compactified theory. So at finite temperature, either of the CP or ZN one-form symmetry should be broken. So, and it gives a very physical result. So this is a two naively possible phase diagram in the temperature and the theta parameter space of the SUN gauge theory around the theta called pi. And this Hooft anomaly states this CP broken line on the theta called pi should reach or go beyond the confining temperature like that. So that this possibility is allowed, but this is impossible. So this is a very beautiful result from the Hooft anomaly for gauge theory. So let's go to the anomaly matching for QCD. NC equal NF, massless QCD in this case for simplicity. And the action is given by this, and A is gauge field, SUN gauge field. And this theory has a flavor and chiral symmetry, which includes this complicated quotient. But we here concentrate only on the subgroups of the symmetries, which includes the vector-like symmetry, this SUN flavor of ZN color flavor, which comes from this part, and the axial Z2N axial symmetry, which is a residual symmetry of the U1A due to ABJ anomaly. And here we want to gauge this vector-like symmetry, but the procedure of gauging the vector-like symmetry is quite similar to that in Yamil's theory. Because after gauging this SUN flavor symmetry, we encounter ZN one-form symmetry due to the existence of this quotient ZN. So we also need to gauge this one-form symmetry where B and C two-form and one-form U1 gauge fields are needed, as with the case of the Yamil's theory. So let's study mixed Hooft anomaly between them. As I said, we first gauge this vector symmetry and perform the 2N axial transformation. And this is gauged action. It includes the flavor gauge field, which is denoted as capital A. And we also put a two-form gauge field, two-form U1 gauge field B is related to this ZN quotient, and perform the ZN axial transformation. And from fermion measure, it gives this non-trivial factor, non-trivial phase. So we have the mixed Hooft anomaly in this case between them like this. So either of symmetries should be broken. And it is consistent with the chiral symmetry breaking of in QCD. But the problem is this Hooft anomaly disappears in the compactified theory because in the compactified direction, the ZN one-form symmetry or the ZN zero-form symmetry appearing in the procedure of gauging the symmetry disappears. So this is the point we have to consider ZN twisted boundary condition. So we here introduce SUN flavor ZN holonomy, which is equivalent to flavor dependent ZN twisted boundary condition. This omega is nth root of unity, and the boundary condition is given by this form. And QCD with this boundary condition is called ZN QCD, which has been studied by several groups, including us. And if you take L to infinity limit compactification circumference to infinity limit, it becomes just massless N flavor QCD. And in this case, we have a ZN zero form symmetry, which was absent in usual QCD, but it is an intertwined symmetry between cyclic flavor rotation and ZN zero form center transformation. So it was named as a color flavor center symmetry, which is denoted ZNS here. So now we gauge flavor symmetry and this ZN center symmetry, and then perform the 2N axial transformation. Then we end up with a mixed anomaly like this, which is smoothly connected to the mixed anomaly on R4. So now we have the mixed Hooft anomaly among center symmetry, flavor symmetry, and axial symmetry. And one of them should be broken if gap exists. So we emphasize that the twisted boundary condition works to make Hooft anomaly survives in compactified theory. And by using this Hooft anomaly, we can make constraints on the finite T-mu phase diagram of ZN QCD. And this is the two possible conjectures. The point is the trivially gapped phase is forbidden. So at mu equals 0.0 line, the chiral phase transition temperature should be larger than or to equivalent the confining temperature. So we can compare these results or these conjectures from the Hooft anomaly with the lattice results, which we have obtained a few years ago. And okay, this is the result of the lattice. This is the lattice results. I will skip these details of the result, but the point is this result, the Polakov loop and chiral condensate result. And it says that chiral transition never occurs below the center transition temperature, and it is consistent with the absence of the trivially gapped phase or the result of the Hooft anomaly matching. So the lattice and the Hooft anomaly results are consistent. And you may wonder why in this case there is no adiabatic continuity. But for feasible way to realize adiabatic continuity in ZN-QCD, please see the paper by Charman, Schaefer, Unsal, and where the heavy adjoint quark, introduction of the heavy adjoint quark is a key point. So let's go back to the adiabatic continuity. I have run the time, but I will try. So let's go back to adiabatic continuity in CPN-1 model on R plus S1. Okay, so first of all, we first study mixed Hooft anomaly on R2 between SUN over ZN flavor symmetry of this theory and the time reversal T for theta equal pi. And procedure is quite similar to QCD. And we, by doing the similar calculation by introducing the two-form gauge field due to this coming from this quotient, so we obtained a mixed Hooft anomaly between two, or the global inconsistency between the theta equals 0 and pi. And it indicates the Hooft anomaly exists both for even n and odd n. And it indicates the spontaneous time reversal breaking at theta equals pi on R square. But the problem is the same, that on R cross S1, this mixed Hooft anomaly disappears. And this is the point we have to consider ZN twisted boundary condition in S1 direction. Then we find ZN zero form intertwined symmetry between flavor cyclic rotation and ZN zero form transformation. And it is called shift symmetry here. And by gauging this shift symmetry and performing time reversal transformation, we find a mixed anomaly, which is smoothly connected to the anomaly, mixed Hooft anomaly on R2. So the mixed Hooft anomaly between them survives with ZN twist on R cross S1, and it is a necessary condition of the adiabatic continuity, but it's not conclusive. So this is why we have to study by the lattice simulation. So what we want to check is the following conjecture. For the periodic boundary condition, there is a crossover behavior of the Polakov loop, which is the ZN symmetry order parameter. But the conjecture says there is no such a crossover. So even for large 1 over L corresponds to the temperature, large 1 over L, or the small L, so Polakov loop expectation value becomes 0. And I don't need to refer to the details of the lattice simulation. We just consider distribution and expectation value of the Polakov loop. And we also consider entropy density. And this is the result of the distribution plot of the Polakov loop. At low temperature, the distribution of the Polakov loop concentrates around the origin. And it reflects the ZN symmetry at action level. And at high beta means a small L tau, and low beta means large L tau. So for small L tau, it forms a regular polygon shape, very symmetric shape. And so in this case, again, the expectation value of the Pollack loop becomes very near to 0. So this means that it has a ZN symmetry at the quantum level. And it is also the case with the other n equals 5. In this case, it forms a polygon, a pentagon. And it is a result of the expectation value of the Pollack loop. Low beta or the large L, so it becomes 0. And even for large beta or the small L, so it is consistent to 0. And so there is some scale around that. So these blue points are the absolute value of the Pollack loop. It is not the order parameter of Zn, but it just indicates how broad this distribution is. And there is some beta, at some beta, so this value gets large. And at this beta, the dominant scale of the theory changes from the lambda CPN to 1/L. So even at high beta scale or the high small L scale, this value becomes small. So this peculiar behavior indicates the stability of the Zn. And it's also the case with the other n. So still, the expectation value of P becomes small after the absolute value of the becomes large. And we also find the fractional instantons configuration by picking up some configurations from this distribution. And we look into the X dependence of the argument of Pollack loop. So it indicates how the vacuum transition take places. And this is the case of n equals 3. There are 3 vacua like this. And if you like the auxiliary line, you can find in the left figure, it is nothing but 1/3 fractional anti-instanton and 1/3 fractional instanton. It is nothing but bion. And the right case is corresponding to the 3 times 1/3 fractional instantons, which is nothing but single instanton. So it means that fractional instantons cause transition among n classical vacua, and which leads to stability of Zn symmetry and adiabatic continuity. And even though this polygon shape is broken at large beta, so adopting a larger sample number or the statistics restores a polygon shape like this and leads to small expectation values like that. So for small n sweep or the statistics, for large beta, this shape is broken. But if you earn more n sweep, so you get the symmetric form, and it leads to small expectation value like that. And we also study quantity corresponding to the thermal entropy density for PVC. In the case of PVC, it is just the quantity counting the number of degrees of freedom, and it's given by the positive number. But in the case of ZN-TBC, the result is given by this for n equals 3 to 20. And it takes a negative value, unlike thermal entropy for PVC. And there is no transition which is like this and which is consistent with adiabatic continuity. And in large M limit, it seems it becomes 0 like that for the whole beta region. And it is also consistent with the volume independence, so which is approved by Sageman-Pasik. So all of these results imply...
We need to finish up soon. So,
okay, so I will
leave some time for discussion.
Yeah, I will finish soon. So all of these results imply Zn symmetry stability even at small compactification circumference and supports adiabatic continuity conjecture. Okay, so I think I have no time to discuss other theories with Zn twisted boundary condition, and Yuya will discuss them in detail in the next talk. So let me summarize. So bion contributions at field theoretical levels with Zn twisted boundary condition yield renormal-like imaginary ambiguity, and which should be cancelled by the perturbative Borel summation. And the Hooft anomaly survives in the compactified theory only with the ZN twisted boundary condition. And the lattice simulation exhibits ZN stability even at small radius, which could imply adiabatic continuity in 2D. And I did not refer to, but other results also indicate ZN twisted boundary condition leads to the adiabatic continuity of the vacuum and phase structure in 2D. Okay, thank you very much.
Thanks, Tatsu. Very nice. Okay, we still have time for some discussion and questions. So if you have a question, please raise your hand. Yes, Metat Unsan, you can unmute yourself. Yes, Metat?
Unmute. Okay.
Yeah.
Yeah, I was talking from my phone, so unmute button did not appear at first. Sorry about that.
Yeah.
So about the renormal singularity, so what happens is that indeed there is a renormal singularity at R2 located at 2 times instanton action divided by n.
Yes.
And the work of Gerald and I did show that there is there's a singularity in the Borel plane at again 2 instanton divided by n, and the so okay, how to say it? So what is the controversy there?
So you mean so without
so there seems to be a controversy people are emphasizing.
Okay.
At least in that case, I do not see any controversy. For example, in pure Yang-Niels theory, okay, what we showed, what we know is that the renormal singularity is at 2 times instanton action divided by 11/3 n. And in the semi-classical domain, we say that it is only parametrically correct. It is again 2 times instanton action divided by n, but you know, this factor of the counterpart of that numerical factor 11/3 for CPN is just 1.
Yeah, sure.
So
point. Yeah.
So and I don't see a reason for controversy. So can you explain that a bit?
Yeah, but okay, the people from Kyushu University calculated some quantity gluon condensates, something like that, in the some regime. But I think this regime is a little bit different from your calculation. So regarding R and lambda, but they calculate this result, this quantity, and find and
I see.
Yeah.
I see.
Yes, and we also calculate the bion contribution, and it leads to some singularity on the Borel plane. And the point is the singularity they find and the singularity we find are different. So but, I think the point may be in the regime, the difference of regimes we have calculated. They do some calculation in a large n limit, and so the regime is quite a little bit different. And or there may be some other reason of such a difference of the renormal or the renormal-like singularities.
If you look to the counterpart of gluon condensate, and if you calculate it in the semi-classical domain, the first contribution that is supposed to be ambiguous is supposed to be complex bion, neutral bion, and that seems to be matching with the what we observe on R2.
Yes, yeah. We also believe if we do the calculation in this regime, so it should be cancelled by the Borel summation of the perturbative series.
Okay.
But it is inconsistent to the large n limit. And some of people, including Takaura-san and Morikawa-san, did the calculation not in large n, and their statement is bion how to say, bion singularity is coming from the prolification of the number of the Feynman diagrams, not from the some specific diagram like renormal. But there is still controversy now. Yeah.
Okay. Okay.
Yeah.
Any other questions? Mita, you still want to ask something? Or?
Unmute.
Okay.
Okay, so also, can you make some comments about the connection between the ZN twisted boundary condition and large N volume independence?
Yep. Oh, so
either in QCD or CPN, it doesn't, yeah.
Yes. So yeah, in the large N limit, if you take large N limit, at least in CPN model in 2D, so you can calculate it exactly. And as you know, the team Swageman particle shows the exact, how to say, adiabatic continuity or the volume independence. And our lattice calculation also indicates that it is correct. So because this quantity corresponding to the thermal entropy, which we call pseudo entropy density, goes to 0 in the whole beta regions. But you know, so this quantity is indicates the anisotropy between x and tau, and in large beta or in large 1 over L, so this anisotropy should be large, but this result indicates it becomes 0. So it is clear indication of the volume independence. And in OD, so we may be able to do the same thing if we introduce the GN twisted boundary condition for fundamental quarks and adjoint heavy quark, as you suggested. And if we do the lattice simulation for that and calculate this kind of quantity, we may be able to find at least large N. So at least in large N, the volume independence of the result. Maybe we may be able to find the adiabatic continuity not in large N, but it's just
okay.
Yeah.
Okay. Thank you very much.
You're very welcome.
Well, Tatsu, I'd like to ask you a question. From the lattice point of view, what do you think are the most natural calculations related to these questions that are actually doable?
So you mean adiabatic continuity?
Yeah. Yeah.
So the point is, in our calculation, we start, for example, from the large compactification circumference, and we change the radius too small. But if you find a very good configuration which makes the ZN symmetry exact, even in the small L region, like the high beta region. So you can use this configuration and as a starting point and going this direction.
Okay.
So it may be the possible way to find adiabatic continuity or to show the adiabatic continuity exactly on the lattice. And we are trying to recently, but yeah, we have not yet obtained the result. But
in which system? In which theory?
In this system, the same system.
Okay. Okay.
Yeah.
So
the main point is directions changed from this or from this.
And are the obstacles mainly numerical, or are there conceptual problems?
Basically numerical. So,
okay.
Yeah.
Okay. Any other questions? Okay, so we finished right on time.
Sorry, so if I have,
yes,
sorry.
Yeah.
If I have
Yes.
3 minutes, so let me
Sure.
advertise for the young researchers around me. So other resurgence projects I'm involved in are given by here. And one of them is the exact results of the 3D supersymmetric chance-sign theory with matters. And this theory, we have shown this theory exhibits very clear resurgent structure and thimble structure. And the other one is the quantum phase transition in 3D n equals 4 QED. And it can be elucidated by the use of thimble analysis and translates expansion. And it is in progress. And this result will appear in arXiv shortly. The relation between Stokes phenomena in exact WKB and standard resurgent analysis, including the bion calculus, is clarified, and where the equivalence of the several quantization conditions, including Gutzler quantization condition, are shown explicitly. It appears soon. And the Schwinger effect under time-dependent strong electric field is also analyzed by exact WKB method, and which is consistent with those of the steep descent Gerald a few years ago did. And the resurgent structure of the non-relativistic quantum system is being studied in a similar manner to the relativistic one, which is inspired by the Marvin-Ray's work. Okay, it's okay, thank you. That's all.
Thank you, thank you. All right, let's thank Tatsu again, and